Hello, ladies and gentlemen. Today we're going to be talking about higher degree functions and mixing in some complex numbers, some imaginaries, some i's, everybody's best friend I, the square root of -1. What you should know so far is that a function of degree 5 should have 5 zeros. So we talked a long time ago about the connection between functions, the zeros and the factors. If 2 is a 0, then x minus 2 is a factor. We're going to expand that a little bit and deal with some imaginary numbers with this example. So our goal for this first problem is to take this 5th degree polynomial and factor it and list its zeros. So first of all, to factor, right away I see something that's going to help us a little bit, is that this thing has a factor of x that's common to all terms. So let's go ahead and get this out of the way. Now, I left something off actually, and it's good because right now I'm at a problem. I don't have a way to factor a 4th degree unless I were to look at it in a calculator or to try a bunch of different possibilities with the rational root theorem. But the thing that I left off is that one of the zeros is 1 plus 2i. All right, so this is a complex number. It has a real part 1 and has an imaginary part 2i. But the fact that that's a 0 just means if I replace x with 1 plus 2i, I would multiply it all out a bunch of times. I would have to raise it to the 5th power and then raise it to the 4th power and multiply by 5 and all that. But if I sub in, let x be 1 plus 2i, I'm going to get 0. Now here's a big fact that you need to have written down. Complex roots come in conjugate pairs. Make sure this is in your notes. Okay? What that means for us is they're not going to flat out say here are 2 zeros, but if they say 1 plus 2i is a 0, then I can guaranteed know that 1 minus 2i is also a 0. So okay, don't confuse conjugates with negatives of each other. It's not -1 minus 2i, it's +1 minus 2i. A conjugate just means the imaginary part is added in one and subtracted in another. The real part stays the same. So if my goal is to factor and remember the connection between factors and zeros, I know right now 3 of the zeros. I've got x, I've got 1 plus 2i, 1 minus 2i. In the past, if I knew a 0, what I would do to find other ones is I would factor that 0 out and factor what's left to get my other zeros. So we're going to learn something kind of cool right now, which is synthetic division with complex numbers. So what I'm going to do next is I'm going to divide 1 plus 2i out of, I'm going to divide it out of the x to the 4th part that already has that x taken out. So the coefficients of the 4th degree polynomial that's left after I take out the x are 1, 5, 1, 15, and 50. Now, this is going to work a lot like synthetic division worked when we first learned about it, except it's going to be a little bit messier for a bit. So the 1's going to drop down like it always did. What did I do next? I multiplied the number 1 by what was in the box, and I get 1 plus 2i. Okay, next thing I would do is add that to 5. Nothing's going to change. When you add 5 and 1 plus 2i, you get 6 plus 2i. When you're adding complex numbers, it works sort of like polynomials. X's and y's don't mix. Reals and imaginaries don't mix. So I get 6 plus 2i. This right here coming up next is the part that's going to take a little bit of effort. What I need to do is multiply 6 plus 2i by 1 plus 2i just like I did. Do this in the margin or somewhere off the side because there's going to be quite a lot of work to show here. But I'm going to FOIL this, 6 times both, 2i times both, and I'm going to get 6 plus 12i plus 2i plus 4i squared. Now the 12i and the 2i make 14i. The 4i squared, you can take out an I squared anytime you want and replace it with a negative sign. So this is the same as negative 4. So 6 minus 4 is 2. So long story short, 6 plus 2i times 1 plus 2i is 2 plus 14i, and that goes here. All right, so don't erase that work from the margin of your paper or wherever, but it's kind of in the way on my screen, so I'm going to get rid of that. And continue. 1 plus 2 plus 14i, 3 plus 14i. Just add the real parts. I'm going to kind of speed this one up a little bit. When I multiply this by this, I'm going to FOIL again, but I'm going to kind of FOIL in my head. I get 3. And then I get 14i plus 6i is 20i. And then I get 2i times 14i, which is 28i squared, which is minus 28. So 3 plus 20i minus 28 is negative 25 plus 20i. Okay, and now let's keep the pattern going. I'm going to add that to my 15. Negative 25 plus 20i and 15 makes negative 10 plus 20i. I'm going to kind of do a quick version of the FOILing again. 1 times negative 10 is negative 10. Then I get a 20i and a minus 20i, so those go away. I have 0i plus 40i squared. And look at that. 40i squared is negative 40, so that's negative 50. Negative 50 and 50 makes 0. So it worked out. The fact that that's 0 means there's no remainder, which means 1 plus 2i divides in evenly. I knew it was going to divide in evenly because they told me it was a 0, and this just confirms that. So you need to get 0 right here. Now, this is where it's going to go from a little bit ugly to pretty again. What was our big yellow rule? Complex roots come in conjugate pairs. If 1 plus 2i is a 0, then 1 minus 2i is a 0. So I want to go ahead and create a new problem where I divide 1 minus 2i into what's left over. Drop the 1 and start the process again. And watch how much nicer this one is. 1 times 1 minus 2i is 1 minus 2i. Add those two. 6 plus 1 is 7. Negative 2i plus 2i is 0. Multiply. 7 minus 14i. The 14i's go away. 3 plus 7 makes 10. 10 times 1 minus 2i is 10 minus 20i. Add those and get 0. Again, this 0 confirms what I already knew, which is that 1 minus 2i is in fact a 0. Okay, so let's go back and sum up what we know so far. This original 5th degree polynomial that I was trying to factor, it's going to be, let's get a copy of that down here. Well, that didn't work. Take that back. I'll just rewrite it. My original problem, which was to factor this plus 5x to the 4th plus x cubed plus 15x squared plus 50x. Remember, that was my problem. It's been a while since we started, but that's what I was trying to factor. I got the x out. That was one factor. When I take my two imaginary roots out, my two complex roots, I'm left with x squared plus 7x plus 10, which factors to, by the way, x plus 2, x plus 5. Now, I know two zeros, the 1 minus 2i and the 1 plus 2i, but what about factors, okay? If they're complex factors like this, it doesn't change the fact that x minus those zeros makes a factor, right? If 2 is a 0, then x minus 2 is a factor. If 1 plus 2i is a 0, then x minus 1 plus 2i is a factor. The other conjugate pair, x minus 1 minus 2i, also a factor. So technically this is in factored form. However, I don't want to leave it like this over here. That's not really pleasing to the eye. So let's clean this up a little bit. My three factors here are all good. Those can just carry on. Now, let's distribute this negative. X minus 1 minus 2i and x minus 1 plus 2i. Distribute that, and now I'm going to distribute each one of these. I'm going to get 9 terms because each one of these three is going to distribute to each one of these three. So my first term is x times x, x squared. X times negative 1, negative x. X times 2i, 2ix. All right, and now I'm going to distribute the negative 1 through all three. Negative x plus 1 minus 2i. And now I'm going to distribute the negative 2i through all three. Negative 2ix plus 2i minus 4i squared. Okay, so multiplying those two last factors together gives me these 9 terms, and some things are going to happen. Let's see. Plus 2ix minus 2ix minus 2i plus 2i. And now negative 4i squared. Remember, an I squared is the negative 1, so let's think of that as plus 4. All right, so now we're ready for the whole thing. X squared, because that's left over. Negative x, negative 2x, plus 1, plus 4, plus 5. All right, so there we go. We factored our 5th degree polynomial with a lot of beautiful steps. Okay, there's a couple, I mean, you could have done rational root tests to say negative 5 is a 0 and gotten the 5 factor, or the x plus 5 factor, and pulled that out. There's a lot of ways to arrive at this answer. Given the info that we were given, which was one of my zeros is 1 plus 2i, this was the way to take. All right, so some big facts came up in this one example. Complex roots come in conjugate pairs. You don't want to leave them as x minus, but just like the fact that if 2 is a 0, x minus 2 is a factor, that will work for both of those conjugate pairs. So that's how I came up with these factors over here. And then you don't really want to leave it looking like that, so multiply it out and get this quadratic. And this quadratic, we would say, doesn't factor to nice, neat numbers. It would have imaginary solutions, so that means that 2 of our zeros are not actually x-intercepts. All right? I'm going to pause real quick, generate a graph, and then come back on to show you that graph. Okay, so here we are on our graphing calculator. This is a 5th degree, positive 5th degree, which means it needs to leave to the bottom left and the top right because it's an odd power. We had 3 good zeros of 0, negative 2, and 5, which made our factors x, x plus 2, and x plus 5. And then the other 2 of my 5 zeros are imaginary, which means they're not going to show up on the axis, the x-axis of this graph. All right, so that's going to do it. What a beautiful graph. Young out.